Okay, so I'll try to speak louder. This research is focused on influence of the measuring capillary. The conversion in such a devices is measured by a small capillary that is inserted in the sample channel. And here, as you can imagine, this capillary influences the flow and can also influence the results of the measured conversion of the carbon monoxide or other exhaust gases. So we are trying to build a digital twin of the experiment using our developed code and try to estimate these possible effects that can be there. There are two main sources of possible errors. Firstly, if the capillary is big or large, then the blockage of the flow is high, and also the conversion in such channel is really higher than the conversion in reference channels. So that's one possible source of errors. The second is that when we use, on the other side, very small capillary, then it's very near the catalytic material, where the local conversion of the carbon monoxide is also higher than in the whole channel average. So we try to find some optimal capillary size and its sampling rate to obtain channel average data of the conversion. So it's ongoing research, and now we are at stage where we try to fit or adjust our kinetic parameters to match experimental data for different capillary sizes and different capillary inlet flow rates. When this everything will be nice and these curves will be on top of each other, then we will try to use our model to predict some optimal configuration of the experimental setup. So it's ongoing research. We are working on it. The last application that I would like to talk about of the developed solver is connected with the industry, in particular with industrial oxychloration process that is usually performed in these types of reactors where a tube that is packed with some Raschig rings with catalytic material is cooled by water evaporation. And we are working with industrial company that owns such reactors, and they have some problems with processes, and they are very curious in temperature on the local temperature on the contact of the Raschig rings with the tube of the reactor, and they tried to calculate it using some empirical correlations, but it was not sufficient because local flow properties are not included here. So we have selected the most problematic zone with highest temperature, and we study it using our solver with kinetics adjusted to oxychloration based on some literature survey. And thanks to it, we can study either local flow field, conversion of the ethylene, and also local hotspots inside the Raschig rings bed and the contact with the tube. That brings me to the end of my presentation, where I would like to conclude. We have developed non-isothermal solver for heterogeneously catalyzed reactive flow. We have verified it against surrogate model in channel scale simplified geometry, and we perform some other device scale simulations, and we are currently working on studying influence of the sampling capillary on measurement results. In the future, we would like to leave assumption of the steady state and try some dynamical simulations. So thank you for your attention, and yeah, I'm ready for questions.
Very nice presentation, Tomáš. So we are now open to questions from the audience. Are there any questions? Thank you. No, he can please repeat the questions. Is your permeability coefficient used, is it homogeneous, or do you always use the same way as metal? Is your permeability going to be homogeneous?
Yeah, the question was if my permeability coefficient that is used here, is same for the whole porous structure. Well, at the moment, we are using the same permeability for the whole device, but it's because we tried in the past some studies where there were several sections where different permeability or these pore scale simulations, we have a lot of different samples with these geometries, and we have several permeabilities that are based on these different samples. And in the past, we tried to use these different samples along the channel, that the permeability on the star was from one section, then another, but the results were quite similar. So now we are using just one permeability for the whole device.
One question to follow up this question, but the permeability was not so much difference between the different points, no? Because we are working with extruded monolith. The process normally should be around applying.
Yeah, the question was if these permeabilities from different sections were different, or I think that there was difference because in some these structures there were big pores, and when this big pore is present, then the permeability of this sample is much permeability is higher. So there were there can be some cracks in the cracks inside the porous structure, and then the permeability is higher. So it was not so same, but the overall results were very similar.
I'll quickly check if there are any more questions in the chat. No, so I take the liberty. All right.
No, it's single phase. So yeah, everything is a single phase.
Is the code published?
Well, we are working on it. We are preparing some GitHub repository where will be everything prepared for your own usage, and published. It will be together, as I said, about application with collaboration with experimenters from Oak Ridge. From this research will be paper, and here will be code published. But it's only part of my master thesis. If you would be interested, I can send it to you.
I'm very interested.
Okay, let me know.
Really interesting. And I have another question, a technical one. How do you are meshing the packet bed? How you are working with the contact area, especially that you work with the transfer?
Well, the packed bed is prepared using, in our group, we have this part that works in CFD DAM and so on. So they have prepared for me a STL file of the bed, and I used Snappy Hex Mesh to create mesh based on STL file. So it's Snappy Hex Mesh.
But for the contact points, they are fused together, all the particles, or?
Yeah, well, yes, they are together. The heat can conduct from one particle to another. Yeah.
You are going to over calculate it. Right. It's something for you only. It's not a critical study. You need to take it into account.
Yeah, I know.
All right, so very interesting discussion. I would just take the liberty to ask you a simple question. The last application that you presented,
Yeah.
was very interesting, but I was just curious, did you study the correlation between the porosity and permeability,
Oh,
or I mean, what is the main parameter for your study?
here in the last application,
last,
you mean the reactor?
Yeah, exactly. Here.
Here we use the Rashik rings are in porous zone where we prescribe some relatively low permeability, and everywhere else is just free channel.
Yeah, so basically, since it's an experimental case, I would be curious to know what is the porosity value experimentally.
Yeah, we have measured it because this company was very interested, so they made some their studies and they give us the data, so we just take it and paste it.
Order of the value?
I think about 0.3 or something like that.
And my question was that since you are considering a constant permeability for the whole thing, right?
Yeah.
So did you study with porosity how the permeability changes and how they're correlated?
Not in this case. I think maybe something in the case with catalytic materials, but it was not me, but maybe some of my colleagues.
Maybe.
Yeah.
Anyway, so let's thank the speaker once again. Very nice.
Hello, everyone. My name is Jiahao. I'm a PhD from University College Dublin. The name of my presentation today is Modeling of a Baffled Horizontal Subsurface Flow Constructed Wetland, Optimizing the Hydraulic Performance. I'll use this?
Yes, exactly.
My presentation will be divided into these 4 parts. Okay, sorry. The key objectives of my work can be concluded in these 2 points. The first one is to obtain the flow field of the constructed wetland. And the second one is to assess the hydraulic performance under different baffle settings. First, let's start with some background knowledge. Constructed wetland is a commonly used green technology for wastewater treatment. And generally, it can be classified into 2 main types according to hydrology: surface flow and subsurface flow. And subsurface flow can be further divided according to horizontal flow and vertical flow. The picture on the right-hand side shows the type of the constructed wetland I simulated. Which is a horizontal subsurface flow. It consists of plant and substrate. The substrate can be gravel, sand, serum site, and so on. Overall, it's porous structure. The water flow into the system, and when it flow out, it can be purified because of the biofilm on the carried on the substrates. However, an unfavorable hydraulic performance, such as short circuiting, back mixing, can significantly affect the treatment efficiency of the constructed wetland. So it's very important to make sure the system has a good hydraulic performance. Let me explain in more detail. Constructed wetland requires a certain amount of time for the wastewater to stay inside the system before it can be purified. this time should not be too long or too short. But in real life, because of the short circuiting or other poor hydraulic conditions, the water particle spend different time in the system. This is called residence time distribution. If we do a tracer study for a tank, and we presume the tank is of ideal hydraulic condition, we inject some certain amount of tracer at the inlet. After some time, we will get the concentration of the tracer at the outlet, like the right-hand side, the blue stripe, like that. But in real life, without ideal hydraulic conditions, the RTD curves shapes would be like that in the middle. Some will stay longer, some will stay very short time. Besides, all the indexes to evaluate the hydraulic performance are derived from RTD functions. The two most important indexes are hydraulic efficiency and dimensionless variance. This picture shows the geometry I simulated. You can see the basic structure of it, the inlet, outlet, baffle, and the dimensions. The whole domain is filled with porous media. And since the geometry is quite simple, so the mesh quality is pretty good. And the right-hand side shows the main approach to my study. Firstly, I used the interfoam to obtain the velocity field. As you know, interfoam is a two-phase solver. So this step can provide the information about the water surface precision. And then I use the scalar transport foam, which is a solver for resolving the transport equation for passive scalar T. This step actually simulates the tracer movements through the tank. And then I simply monitor the scalar T at the outlet in ParaView to obtain the RTD curves. Ultimately, all the indicators can be calculated based on RTD curves, and then the hydraulic performance can be evaluated. This is the basic porous media theory in my study. Porous media is modeled by attenuating the time derivative and by adding a source term to the Navier-Stokes equations. In my case, I use FE options to add Darcy-Fortimer equations as a source term. And I use these two empirical formulas to calculate the coefficients C1 and C2. In OpenFOAM, we always define these two coefficients in FV options. These two tables show the main setup for my case. The porosity is 40%, and average particle size is 5 millimeter, which should be converted to the values for D in FV options. And the boundary conditions for inlet U, as said, the flow rate inlet velocity 0.006 meters cube per hour. So the nominal residence time is 28.8 hours, which means that when water flow into the system, each single particle theoretically should be stayed in the tank for this long, 28.8 hours. And I said the T value for one, generally, there are two most used methods for injecting the tracer, which is pulse input and step input. In this case, the value for T was kept constant during the simulation, so it can be considered as a step input. This table shows the combination of the parameters, the baffle parameters the combination of baffle parameters in my simulation. In my study, I mainly tested two baffle parameters, which is baffle length and the number of baffles. In these cases, the flow rate and inlet-outlet configuration and porosity were kept constant. So there are 30 scenarios in total, and I also test one case without baffle inside. Here are the results for the flow field. The flow behavior is quite important for the constructed wetland because it has a huge impact for the biological processes within the constructed wetlands. Since the contaminants movement and residence time is determined by the velocity field. These 5 figures, they all have the same baffle numbers, but the baffle length are different, ranging from 0.4 to 0.58 meters. And you can see they all have the very similar, the same relative high velocity area near the inlet, because due to the same inlet setup. And they also have the same high velocity zone at the end of the baffle, the inner band there, especially for the case C4 and C5. It's simply because the smaller cross-sectional area caused by the longer baffle. And the velocity for the dark blue area is 0 or extremely low, representing the dead space in the reactor. We can see the depth, most of the dead space concentrated at the corner in the reactors. This figure shows the result from another angle. These four, they have the same baffle length but different baffle numbers. The baffle length are all 0.5 meters, and baffle mount from 1 to 11. It can be clearly see that the cross-sectional velocity noticeably increased as the baffle amount increased. So in conclusion, the baffle amount has a significant effect on the cross-sectional velocity and is conducive to reducing the dead space. And based on the result from CFD and by monitoring the T value from the outlet, we can get the RTD curves like this. The shape of the RTD showed in the figure 4 is exactly what I expected before. The concentration rapidly grow to the maximum and then gradually decrease to the initial value. And if you look at the figure A and B, when the baffle length is 0.4 and 0.45 meters, as the baffle amount increase, the RTD curves almost keep unchanged. And there is a slight change in the case the baffle length is 0.5. But when the baffle length is 0.55 and 0.58, the RTD caves change a lot. It becomes taller and narrower, which means that it's closer to a more ideal plug flow condition. And this is also from another angle. They all have the same baffle amount, but the different baffle length. You can see when the baffle amount is 1, the RTD curves doesn't change. And when the and there's a slight change in the case of 3 baffles. And so what we can get from here is the 2 parameters here, baffle length and the number of baffles, they all have to reach the certain amount. Then we can get a good hydraulic performance. I mean, if one parameter is small and we increase another parameter, the RTD curves doesn't change. It will not significantly change the RTD curves. And as I mentioned before, there are some indicators to evaluate the hydraulic performance of constructed wetland, the hydraulic efficiency and the variance. We can see from the picture, there's the picture A shows a gradually rising trend, except the case with the 0.4 meters baffle. And however, you can see overextension, the baffle length or the baffle amount cannot benefit the hydraulic performance, hydraulic efficiency. And for the right-hand side picture, the variance, this indicator describes the gap between the real flow pattern and the ideal flow pattern. So if the variance is 0, it's the ideal plug flow condition. So this indicator, the smaller, the better. You can see the similar trend is shown in the right figure. Overextension, the baffle length and the number of baffles cannot significantly reduce the dimensionless variance. This is the main conclusions of my research. First is baffles are effective and reliable devices that can be used significantly reduce short-circuiting and dispersion and keep the dead zones to a minimum. The second is when the baffle length is greater than 0.5 meters, increasing the number of baffles has a significant positive effect on the hydraulic performance. Besides, when the number of baffles is greater than 3, increasing the baffle length will improve the hydraulic efficiency significantly. The last one is the best combination of the two parameters is 0.55 meters baffle length and 7 baffles. In addition, excessive extension of the baffle and increase in the number of baffles do not significantly improve the hydraulic efficiency and reduce the dimensionless variance. Thank you for your attention.
Thank you, Jiahao, for the nice presentation. We are now open for questions from the audience in persons. Are there any questions? Please. Could you please repeat the question?
Considered using the mid-age formulation of U. So this is a steady state formulation that computes the residence time distribution.
Sorry, could you repeat your question? Sorry.
Using the mid-age formulation of
Yeah.
U. This is a steady state formulation that is equivalent to
Steady state.
the non-steady computation of the residence time, and it just adds some equations to the Navier-Stokes equations.
Yeah.
So convection diffusion equations for moments of age, and then you get the first moment is, for instance, the residence time. So you have a local residence time distribution.
Yeah.
Have you tested this or not?
This is the steady state. I didn't consider the. I haven't considered the unsteady state condition so far. So I plan to test the effect of flow rate later when the flow rate change during a certain amount of time, and we can see the effect to on the residence time curves.
Any further questions?
Yeah, what is the purpose of having high variance on your last results? So I get why the figure on the left, kind of hydraulic efficiency, I get why that needs to be high. But what's the role of the variance?
The role of the
variance.
variance. The variance indicates the dispersion and mixing condition in the tank. So the variance, if the variance is bigger, then the back mixing and is there are more back mixing in the tank. Yeah.
I'll quickly check if there are any further questions in the chat. I do not see. So I will take the privilege to ask you a question. So you showed the velocity plots for different configurations, right? So my question is that I just wanted to confirm, in all the possible configuration that you have studied, the flow field is steady.
The flow field is steady, yeah.
Yeah. So did you interpret it something that if you observe the vorticity field, something whether they have any role to play in the hydraulic efficiency or any physical insight from the flow field? Did you?
Sorry, I didn't follow your question.
Did you interpret some physical insights from the flow field that how the flow field play a role in moderating the hydraulic efficiency? So
mean-
I will rephrase the question. The velocity plots that you showed, can you go back to that slide? So
Yeah.
what can we infer from them that in terms of what role the flow
Field. What's the role of flow field?
field? Yeah.
The scalar transport form requires a given velocity field to calculate the transport equation. So we need that velocity field.
Yes, but can you go to the slide?
Okay,
Actually,
okay.
my question was slightly different. Yeah, here, let's say, so if I consider this analogically as a vorticity field, this is a velocity field. So the strength of this flow velocity, as you told, like, did you study if they have any role in mixing or any other physical phenomena that you are studying?
The velocity field can just let us know where is the low velocity area, where is the relative high velocity area.
Okay, so if there are no further questions, let's thank the speaker again. So I will now invite our next speaker, Dr. Aurélie Louis-Napoléon, and she will be speaking on the optimization of an active device for preserving integer.
Okay, thank you. So hi everyone, I'm Aurélie Louis-Napoléon. I'm a postdoc at Légy in Grenoble in France. I work with Philippe Séché and Thierry Bonamy from Légy, and with Sylvie Travers and Juliette Chastanet from the Birdjab frame of the Ginger Group. So we work all together on the frame of the barrier project on the optimization of an active device for preserving indoor air quality. So let me introduce you the subject. We pass more and more time inside, so the air quality is very important. And one source of solution is one source of pollution is our inside chlorinated solvent. We can find them in former industrial fields, but there exist various devices to protect us from soil pollution, and one of them is the subslab depressurization SDS systems. How it works. So if we take a classical case, we have the atmospheric pressure, which is higher than the building pressure. And if we have polluted soils, in fact, since the atmospheric pressure is higher than the building pressure, air comes from the outside and goes inside and takes some pollution on the way. So air pollutes the indoor air. So to protect us, we can use a subslab depressurization system. And the idea is to put the system below the building, so before it's built. And the pressure inside the system is lower than the pressure inside the buildings. So we can catch all the air and reject it outside. So it consists on a layer of gravel and on the system itself. So in fact, it's a system with a geomembrane. So it's a layer impermeable. And below we have a geotextile. So it's a porous media with various drains. So drains here are in yellow, and the drains are corrugated and perforated, and these drains are connected to a pipe, and this pipe is connected to a fan to suck all the air and reject it outside. So we have to have differential pressure between the drain and the atmospheric pressure of less than Pascal, and there don't exist any advanced method for sizing the system, and specifically for large buildings. So parameters in play are the permeability of the soil and of the gravel, the fan power, how much we have to impose as flow rate, and all the drain feature, as all corrugation, drains number, and spacing between drains. About modeling, we have to model porous media, the gravel, the soils. But non-porous zone as well, because inside drain and inside the pipe, it's free air. We have to model turbulent and laminar regime. So in the pipe, in the bigger pipe, we are turbulent, and in the drain, we are laminar as well in the porous media. So about the barrier project. So the founder is Adam, is a public organism in France who cares about ecological transition. The project investigator is BirdJap. So BirdJap with La Métropole du Grand Lyon, TerraGeos, and Terra Environment work on the experimental platform. So they have a wheel polluted soils, and we put an experimental platform above. So it's a platform with various drains connected to various pipes, and they measure pressure in the drains, in the pipes, and between the soil and the gravel, and they measure velocity in the pipes too. At LEGI, we deal with numerical simulation with OpenFOAM, and the main advantage is we are able to model both the source scale, so the meter scale, and the centimeter scale, so the drain scale, in order to better understand the flow pressure relationships. So the main goal of the project is the development of an active SDS sizing tool. About numerical method, we use Salome for geometry and mesh, OpenFOAM for computation, and ParaView, Python, and the module FreeForm for post-processing. About the solver, we use the PimpleFold solver with Darcy for Scheimer-Singh term through FV option and the K-omega SST model for turbulence. So we solve this equation, and we have a Darcy for Scheimer-Singh term at the end. And these terms need two new input parameters, which are D and F, connected to the permeability K and constant CF. Now about the result. So first of all, I start with drained without porous media. And the first question is how to model a perforated and corrugated drain, because holes and corrugation around the drain are in the millimeter scale. So it's too costly numerically to model them. So the idea is to consider the corrugated and perforated wall as a porous wall. And the equivalent permeability of this porous wall takes into account both the corrugation and the hole. And the question now is, how is the value of this equivalent permeability? So to find it, we compare with experiments performed by BirdJap, and the numerical setup is here. So it's an axisymmetric setup. We impose the flow rate at the inlet. The first part of the drain is smooth, and the other part is perforated and corrugated. So it's a porous wall in dotted blue, and we have air around the drain. So it's we consider the wall drain as a porous media, so we need a thickness, and we choose the thickness as a difference between the exterior radius and the interior radius. Now about the result, so here it's pressure on the drain. The blue points are the experimental results, and we plot various curves, so various numerical results with various equivalent permeability, and we find that the purple one fits perfectly the experimental point. So to conclude on this part, considering the perforated corrugated drain wall as a porous wall is valid, and we found coupled thickness and equivalent permeability to fit experimental results. Using a K-omega SST model to model the flow along the drain seems valid, even in laminar regime, but we don't have any formula to calculate the equivalent permeability. We need to do a simulation and compare with experiment for each type of drain to determine the equivalent permeability. So now if we vary the flow rate at the inlet, and if we keep the same equivalent permeability for each flow rate at the inlet, we see here that at low flow rate at the inlet, the numerical result doesn't fit anymore with experimental results. So we need to adjust the equivalent permeability for each flow rate at the inlet. So here we determine low. So the equivalent permeability in function of the Reynolds number. So the equivalent permeability depends on the Reynolds number at the inlet. So now we look at various out-of-soil drains. So it's the same idea as before, but now we have 4 drains connected to a bigger pipe. And we impose the flow rate at the inlet of the pipe, the yellow pipe. So in fact, the flow rate at the inlet of each drain is different. So we need to have a different permeability for each drain. So here it's results. So at the top we have the velocity along the yellow pipe. So and the point are the experimental data, and the curve it's numerical. So and at the bottom it's pressure, numerical and experimental. And we see that our numerical results fits quite well experimental result. And we do the same things for the drain. So at the top, it's a Reynolds number along the drains for the first drains. And we have pressure along the drains too, and experimental point. So we plot the new equivalent permeability we put for each drains, and we put them on the previous curves, and we see that okay, we don't exactly fit the curves, but the equivalent permeability is on the same order of magnitude. So we need to do more comparison with different flow rates for the multi-drain case. So now if we look at wet drain in porous media with time, so it's more like the SDS systems. So we have various porous media. We have the soils, gravel, the geotextile, the drain. So we impose the flow rates at the inlet of the drains. So air comes from the outside and goes inside the drain. So the blue graph, we have the streamlines, and we see that the streamlines are deviated by the transition between the soil and the gravel. And on the right, it's a pressure, differential pressure between the drain and the outside. And we see that we have like 10 Pascal in the drain, so it's that we want. And the question now is, okay, can we find a relationship between the flow rate at the inlet and the pressure along the drains and the various parameters such as permeability, viscosity, and size of the system? So to find this relationship, we determine a dimensionless number, lambda, as the pressure over the viscosity and the flow rate multiplied by an equivalent permeability over an equivalent length. So the idea is to divide the system into subparts, and each part has an easy airflow path to compute the equivalent permeability over the equivalent length. So we have an 8 for the soils, then in purple a semicircular way in the soils, then an 8 for the gravel over the permeability of the gravel, and then the same thing for the thickness of the geotextile and the thickness of the drain. So if we vary various parameters in the system, so we vary the permeability for the drain, permeability for the gravel, permeability for the soils, and size of the systems. And we find that most of the curves give us the same lambda, so lambda around 0.4. And we have some curves deviate from this lambda, and we can explain this by the fact that so the extreme curves has a bigger ratio, a bigger permeability ratio than the other, and with that we explain that the lambda is a little bit different from 0.4. Okay, so we find a lambda and a relationship between the inlet flow rate and the pressure and various parameters of the systems. And the question now is, are we the same relation in the case with various drain? So to conclude, considering a perforated and corrugated wall drain as a porous wall pipe is valid, as well I used people form solver with a Darcy-Forshaimmer term and a K-omega SST model. We find a relationship between the equivalent permeability and the flow rate at the inlet, so Reynolds number. We find same order of magnitude for various out-of-soil drains as the previous law. And we find, in the case of one drain in porous media, we find a relationship between the flow rate at the inlet and the pressure. So the next step is the comparison with measurements made on the experimental platforms. So questions are, what is the relationship between the flow rate in the drain and the pressure along the drains? And what is the flow rate distribution in multi-drain case? So thank you for your attention, and I'm now ready to answer your question if you have any.
Thank you, Lee, for the nice presentation. We are now open for questions. Are there any questions from the in-person audience? No, so I'll quickly check if there are any questions in the chat. I guess no. So
okay.
I'll take this time to ask you a few questions. So I'm actually curious that you mentioned that in the two parts of different geometries, you have laminar flow and the columns flow. So I was curious, did you take a different treatment to the mess in those two regions, or it's the uniform?
No, uniform.
And what is the difference between Reynolds number in those two regions?
Okay. Okay. Okay, we can see here. So, okay. So it's the inlet of the, it's here in fact, in the inlet of the drain. So we have an high Reynolds number at the inlet, and then it's laminar, the transition to laminar region.
Right. So did you use any turbulence modeling technique?
Yes, in the case it's a K-omega SST model.
Okay, right.
Yeah.
So and another question is the porous media source term that you have added. You didn't incorporate the effect of porosity in terms of the big fan terms, like in the convective term in the time and in the temporal term. Did you consider the effect of porosity term, epsilon, other than the FD option?
The porosity of the media, no, because we have it through the permeability. Yeah,
okay,
yeah.
But you cannot control that.
No.
Right. All right. Thank you. If there are no questions, let's thank the speaker again. Oh, there is a
quick question. This relationship for the line you talked at the bottom, is this just one from the literature?
No, it's a fit, yeah, for the data, yeah.
Did you validate the FD options against
yeah.
The literature?
Yeah, I test some classic Darcy case with just a porous media, and I checked that we found the same. Yeah.
And so, what was the what order of magnitude of discretization did you use?
Okay.
10 to the minus.
Okay, I know I have 8 cells in the thickness of the wall drain. Yeah, so it's right. It's 2 2 millimeter thickness divided by 8. I think it's
Sorry, speak a bit louder.
yeah, it's 2 millimeter thickness for the wall drain.
Yeah.
And I took 8 cells in this thickness.
So the entire drain was only 8 cells across. Or something.
Yeah.
That's correct.
Yeah.
Okay.
All right, so let's thank the speaker again. Hello everyone, I'm Chandan. I'm currently a postdoctoral research associate in the University of Edinburgh, and today I will be speaking on our ongoing research project of flow past stationary and freely falling porous bodies. And this work is funded by European Research Council on the project Dandy Drone. And although this session is bit on the details of the porous media, but I am a person working on aerodynamics and fluid structure interaction. So my talk will be mostly focusing on the aerodynamics and flow structure around a porous body and free falling porous body and its flight dynamics. So let's go ahead. So let me give you some motivation why we want to study this. So we are really fascinated about this beautiful flower, dandelion, and if you can see the fruit and its evolution, I will take you to the end of it. Now, this is the flower of it, and then when it goes to the seed, it actually adapts a very fascinating seed propulsion mechanism through the unique structure of its seeds, which is composed of a parachute-like structure, which is called pappus on the top, and the seed is projected towards, connected by a thin stem. And we take this interest from this natural biopropulsion system. And if you see this video, like when a gust appears and they extract the flow energy from the gust, and most of the seed goes away and falls down within very near distance, but there are some fortunate ones which takes the advantage of the gust and they can propel themselves for a long distance. And as I said, 99% of the seeds falls down very near to the original start of their flight, but some of them which can actually go for a long distance to propel. And so this stems the motivation of this study. And this is some of the biological parameter that you will be interested to know. The most interesting parameters are the porosity, which is 0.9. So it's very porous structure, the pappus, and its terminal velocity is around 0.4 meter per second. And the Reynolds number in the experimental case measured to be around 400, the order of hundreds. So when in the previous study from our group, when we studied the flow structure behind a stable position of this dandelion, we observed and discovered a very unique feature of the stable flow, which is called separated vortex ring. As you can see that why it is, it's not working. So why it is separated, because you can see the vortex ring, which is stable at this Reynolds number, is not attached to the pappus. That's because of the porous structure of the pappus, and there is a separation between it, which makes it stable. As I will give you some more example, that these are the 3 examples of 3 different cases. One is the real biological dandelion seed, one is the replica porous structure, and the last one is the solid disk. And if you see the flow visualization, that in the case of the real dandelion and the replica pappus, we see the stable vortex ring which is separated. However, if it is a solid case where the porosity is 0, at this Reynolds number, you see the flow to be very unsteady, and it is also attached because it's solid, its porosity is 0. And this is a map that we could get, that what is the region of the stable critical Reynolds number where this vortex ring would be stable with respect to porosity. So if we keep reducing the porosity, it go towards the behavior of a solid disk, and you can see the critical value. And in an essence, to give the motivation, to end the motivation, I want to tell you that with the increase of the Reynolds number, the drag becomes constant, and the terminal velocity of the seed is only a function of the wing load and no more depends on the drag value. But we are interested in the region where basically dandelion flies in and around 300 to 400 region. And going to that, now I'm not an experimentalist, and this was a motivation, maybe a bit long, but now I come to the modeling section. Now, how to model this external aerodynamics and fluid structure aerodynamics of this system? There are two approaches. One is micro scale approach, another is macro scale approach. Now, it's no doubt you can understand the micro scale approach is very difficult to model because of its high requirement of very small scale cells. And I will show you some of the examples where we need huge amount of computational effort to correctly model the flow around it. So we take another approach, which is macro scale approach, where we consider the pappus to be a porous media, and then we study the flow field around it and try to understand the dynamics of it. Now, the next interesting thing for the dandelion case is that you can see that the position of the center of mass has a huge effect on its flight for the dandelion case. As you can see in these two cases, either it can be homogeneous, where the center of mass can be situated within the body, like it happens for other many auto-rotating seeds. But for this kind of plume seeds for dandelion, we see that the center of mass is situated at an offset to the center of buoyancy. So which I will show you how it affects the flight dynamics of dandelion. Now, this is the computational challenge that I was talking about in the microscale approach, that if we try to put at least equivalent number of the filaments or bristles in our computational model and try to imitate the diameter to two diameter ratio, which is one of the diameter of the filament and the diameter of the pappus, we ended up into an instant number of cells, which is not manageable, and the computational time is huge because we want to simulate the behavior of the seed in the presence of the gust. So we have to keep the domain size to a bigger amount to understand where it goes, and which we cannot afford for large number of simulations. This is one example where I failed. Like, it's very difficult to capture this flow field. So we took the second approach now, but this is one example of the micro scale structure where I simulated and find out what is the terminal velocity when in one region it falls steadily. And this simulation up to find out when the vertical velocity of the seed reaches to the terminal velocity takes a huge amount of computational time. So which forces us to go for the second approach, where we model the pappus to be a porous media by using the same approach as the previous talk explained, by considering the two sync terms of Darcy and Fockmeyer sync terms. And I also considered the effect of the porosity terms in the temporal and the convective term as the Brinkman term. And the dynamics, when the body is freely falling, the dynamics is governed by the standard Newton-Euler equation of motion with 6 degrees of freedom. And in this case, the two important scales for particular to this problem is, one is the length scale of the problem, which we took the diameter of the body, diameter of the disk, and another is the reference velocity. We take the gravitational velocity of the freely falling body, and using the gravitational velocity, we define the Galileo number, which governs the physics of the body, and the non-dimensional Darcy number, which is a function of the permeability, gives us the effect of permeability on the flight dynamics. So I'll quickly, this is a very simple modification of the code, so I just won't spend much time on it. But for the stationary body, we just took the basic scalar transform form or basic icoform and then modified the governing equation I just stored and coded it so that and we named it as porous icoform, and we validated it with respect to the flow field behavior behind the body, and we got very good match in terms of validation. But I'm more interested in the physics, so I'm not going into the details of that. And so I just hard coded the governing equation into the U equation every vector matrix, and as simple as that. So the coding was pretty simple. And these are some of the non-dimensional parameters for the study that I consider. One is the non-dimensional mass ratio. Everything is non-dimensional here. So M is the mass of the structure divided by. I consider two different cases. One is the homogeneous case where which I denote it by ID. That means when the center of mass is within the body, and IO when the center of mass is displaced. So the moment of inertia for these two cases with respect to the reference system will be different. So I compare the flight dynamics of these two cases, and D is basically here, as I have already given in the schematic, that D is the distance of the center of mass from the pappus, small d, and normalized by the diameter of the disk. And chi is the aspect ratio of the disk, diameter divided by the thickness, which is 10. And Galileo number, I consider 150, from a range of 50 to 150, which falls within the flight dynamics of dandelion. And we consider a Darcy number of 10 to the power minus 4. And this is the 2D result. So first we studied the flow field and tried to imitate the flow field of the experiment by considering a porous flat plate. And we studied the different topology of the separated vortex rings by keeping the porous flat plate at different angle of attack. And as you can see that the experimental flow field is very well captured, even in the 2D case, qualitatively, that for a porous 2D flat plate, we get a separated vortex ring. And you can see that as we increase the angle of attack for a particular Darcy number, we can see that at a higher angle of attack, these nodes and saddle points pairs, they merge with each other, and then finally they result in a tortuous kind of streamline pattern where we do not get any core of this vortex ring. Now, the interesting thing that we wanted to understand how this flow topology changes from 2D to 3D, and we see that qualitatively the topology remains same, but there is a significant difference in a quantitative sense of Reynolds number, that the 2D flow field only gives us a stable vortex ring at a very low Reynolds number of 30, but when we go to a Reynolds number of 130 equivalent to the experiment, the 2D flow field becomes unsteady and their vortex trading happens. But in 3D, we still see a stable vortex ring. And as we change the Darcy number, makes the disk more and more permeable, the distance of the recirculation bubble from the pappus increases and the size of the recirculation bubble becomes smaller and smaller, and slowly it disappears. That means at a very high permeability, the flow will just pass through the body and there will be no recirculation bubble in the flow field. So to summarize the comparison between this 2D porous flat plate and the 3D porous disk, I can say that quantitatively the length of the recirculation bubbles are very different from the 2D to 3D case because of the three-dimensionality of the problem. And at the same Reynolds number, when we change the angle of attack, we see clear distinct node and saddle pairs for the case of 2D porous flat plate, but in some case of high angle of attack in the 3D flow field, those pairs are no more distinct, and we see a merged situation of tortuous flow field. So next I come to the free falling case. So to simulate the free falling case, I adapt the overset meshing strategy, which is available in OpenFOAM, and then I modify the over-pimpled DIM solver equivalently to a porous over-pimpled DIM foam solver, and then I use several refinement zones to get the resolution of the flow field around the body. And this is an example of how my domain moves in 3 different meshes: component meshes, the overset meshes, refinement zone, and the background meshes. And this is an example of a 2D falling plate case where we see that for this particular Reynolds number and moment of inertia, we see a chaotic falling dynamics and very nice evolution of the flow field where the plate starts to flutter and slowly the flutter triggers the tumbling mode, and we see a combination of the flight. Now, our interest was to understand what happens when we give a sudden gust and how does that plate behave. And so this is an example of a ramp discrete gust, and we see, and we give a vertical velocity initially almost equivalent to the estimated terminal velocity so that the plate does not move. In the transient phase, it slowly goes up. Then when we impose the gust on it, we see how this separated vortex ring, or in this case, it's not separated because this particular simulation is with impervious body. So it was the first test case to test the 6 degree of freedom solver and validate it. And we see that slowly this vortex ring gets distorted and gives rise to a very nice vortex shading, and we basically see the plate with the leading edge and the trailing edge vortex, which gives sufficient lift to the body to keep itself afloat, extracting the energy from the flow. And this is the same thing that I understand, and it's an in-depth analysis of how these nodes and saddles behave and how they change to give rise to the leading edge and the trailing edge vortex. Now the interesting part comes. What happens when we change the Galileo number? What change in the dynamics we see? So here in this case, you see 3 different cases. One is Galileo number 50, 100, and 150. And when the center of mass is situated within the body. So this is not the case similar to dandelion, but it's a homogeneous case. And interestingly, we see that in 50, and in every case, we give a horizontal initial condition, a horizontal velocity to disturb it, so that to see whether it comes back to its stable position or not. So in the Galileo number 50, it basically goes, flutters, and comes back nicely and falls steadily ultimately. And in the Galileo number 100, we see a stable fluttering regime where the plate flutters like this and stays in the stable regime. And in Galileo number 150, the initial flutter increases in amplitude and gives rise to a tumbling state. And you can basically visualize the modes in this picture. So the first picture shows that in the transient mode how the plate behaves. And in 3 cases, one is the steady fall, another is the steady flutter, another is flutters, and then it results in tumbling. Now, this is the most interesting part. Now, in the nature, how we see stable flight. So this gives us some sense of understanding that when we change the center of mass to an offset from the pappus, that means here the center of mass and the center of buoyancy is no more the same point. At the same Galileo number, where the homogeneous case was basically giving rise to a tumbling state, we see that the body initially after the transient comes back to a steady fall because of this offset distance. So this gives us a hint in how the passive flyers, by putting their seat at an offset, stabilize their free fall. So this is the amplitude of the vertical velocity. You can see for tumbling, there is a very oscillating and aperiodic velocity. But for the second case, where the center of mass is below, you can see it comes down to the terminal velocity very soon. Now, the same case at Galileo number, we came down to Galileo number 50, where both the cases are basically stable and comes back to the steady fall regime with a particular constant terminal velocity. And then this case shows us what happens when we keep the body falling and let it fall with the terminal velocity. And when we are sure that it is falling with the terminal velocity, we put the same ramp gust to see how it behaves. And in the response of the vertical velocity divide and plotted against the non-dimensional time, you can see that, don't know, it's not working. So up to this point, it slowly reaches to the terminal velocity. And then from this point, we impose the ramp gust, and which shows us here that here the case is a case of gust ratio 0.5. We see that both the cases goes to a transient phase and oscillates, and then slowly it again comes back to a constant velocity. But the interesting fact is that whether the constant velocity slows down or not, which is an ongoing investigation. But the difference between these two cases, whether the center of mass is at an offset or not, we can see that the transient is almost negligible for the case where the center of mass is at an offset. And this is for a higher gust ratio, where we can see that the transient is, the amplitude of the transient is much higher, of course, intuitively, but it clearly shows that when the center of mass is at an offset, the transient is almost done and it slowly damps down to the terminal velocity. And this is another interesting case where the gust is a continuous periodic fluctuation. We do not give a ramp, but we keep it oscillating. We can see that the body oscillates aperiodically and for a long transient time around its vertical temporal velocity. And the similar behavior happens for the higher gust ratio. However, we see that the transient is much shorter, and then the body tries to settle down around its terminal velocity. So this is a basic idea of how the trajectory falls of these two cases. So basically, when the continuous gust is there, it does like this and keeps on flying till the transient is ended. And so this is up to this is the present state of the work that we but I want to tell you that all these studies are done with relatively coarser meshes, because it's a huge intensive computation, and we are slowly trying to develop a methodology of a refinement zone which is falling with the body, so that we do not have to keep it fine everywhere or for a long distance, so that we can understand what is the impact of this motion on the vortex ring and what is the actual flow physics underneath. Thank you, everyone, and I will be happy to answer any questions you have. So I acknowledge that these simulations are done in Cyrus and Archer 2, and it's funded by access to HPC grant. And this is some of the contacts if you want to ask your questions further. So the floor is open for questions. Thank you. Please.
Are there any biological impacts from your findings?
What do you mean by impact?
I mean, because it does a particular thing, has a particular behavior, does that change anything about the distance the seed goes?
Yes, exactly. So that's where we are trying to, of course. So as I showed in the video, some of the seeds keep themselves afloat for a long time, which means that they basically slowers their descent and then goes for long distance with the gust. But other case, 99% seeds falls within a near distance. So we try to understand for that particular case, what is the impact of the gust and how it extracts the energy from it. So there are a lot more to study and further, because when I show you the tumbling dynamics, it depends when we should give the gust so that it goes to the maximum distance, or like this kind of impact. So nature does it excellently, but it does with a selection of the seed of 1%. We are trying to understand how that 1% of seed goes to the maximum distance, so that the picture that I showed, the manufactured prototype of dandelion that we are going to test in the wind tunnel. Yeah, this one. So if you see this picture, it is the manufactured dandelion, a manufactured drone in our lab, which is very small scale, exactly in the scale of the dandelion. And we are going to test it in the vertical gust wind tunnels and understand how it behaves and try to model it through simulation to understand the flow. Right. Yes, please.
Yeah, really cool work.
Thank you.
Could you speak a little bit about how computationally intensive it is? I remember you said that.
Yeah, of course. Of course. So the 3D cases where I apply gust, the computation, so currently it has a scale of around 10 millions, but it still coarse in terms of capturing the resolution of the flow field. So I basically use Archer 2 of 2 nodes, let's say 128 processors each. So basically 256 processors, and it runs for 5-6 days to capture the sufficient distance that I want to capture after reaching the terminal velocity. And one thing is very important to mention is that when it falls freely, the computation is much faster. And then suddenly when I give the gust, its local CFL number criteria changes and the time step goes to a very small number and it takes much time. Thank you.
You consider like non-uniform porosity, so that like you did take a look at this picture, like in the center, like the porosity is relatively low.
Yes, so it is quite well known that the permeability, I would say in my model, the permeability is variable radially. I don't know about maybe the porosity, sorry, it's porosity which is variable radially and which has a correlation with the permeability and how the permeability changes. But yeah, that is something to study. Currently in my model, permeability is kept uniform in 3 directions, but since we are inputting permeability as a tensor, we can code it to behave in a different way, but we need more data from experiments on how the permeability changes with the radial variation of the porosity. There are some empirical formulas considered in the literature, but it's not so robust for every application. Thank you. I'll see if there are any questions in the chat. There are no questions. Are there any more questions for me? You can email me also if you have further questions. So we'll quickly go to the last speaker. Thank you. The last speaker of the session. So I invite Mr. Ranjith Khumar, and he will be speaking on numerical modeling of liquefaction around marine structures. So I'll set it
up. Welcome everyone to my presentation. Let me start by introducing myself. My name is Ranjith Kumar Shanmugasundaram. I am an engineer at Wikki GmbH and also a PhD student at TU Braunschweig. In this presentation, I will be taking you towards the numerical modeling of seabed after residual liquefaction. And here are my co-authors. And the menu, what I have for today is, first, I'll be introducing you what is meant by liquefaction, and then about our project. And then I'll be taking you towards the numerical model that I have implemented for this project. And then I will be taking you towards the 3 different case studies, what I have been done using this numerical model. The first one is where I compare my numerical model against the analytical results. And the other 2 where I go much detail, much complex, that where I cannot compare against the analytical results and I cannot be using the analytical solutions anymore. And finally, I'll draw some conclusions and future work. Okay, what is liquefaction? Some of you may be already familiar with this concept, but for those of you who aren't, I'll briefly explain it. Liquefaction is a process in which soil behaves like a highly viscous fluid. This happens mainly in case of a saturated soil. The saturated soil is a soil in which the soil skeleton is completely filled with water. And this water exerts the pressure on the soil particles, which is known as the pore water pressure. And this pressure helps to have the soil particles attached to each other. And this also exerts the shear stress between the soil grains, which helps the soil particles to withstand heavy loads. For example, a breakwater like here, and also a gravity anchor. And whenever there is a load on the seabed, for example, waves, you can see that because of the waves, there is a load on the seabed, and then the soil squeezes. And if you have a drain condition, the water molecules can freely go out of the soil particles. And if there is an undrained conditions, the pore pressure, because of the load, it starts to build up. And then at some point of time, it doesn't have time to go out of the soil particles, and then the pressure starts to build up. And in that case, the soil weakens, and then it can readily move with respect to each other. So at some point of time, the pressure between the soil particles goes high than the initial effective stress of the soil, which helps to keep the soil in contact with each other. And in that time, the soil weakens, and then it can readily move with respect to one another. So in that case, the soil loses its capacity to withstand heavy loads. And for example, here the breakwater, it collapses, something like this. So that brings us to our project New Limas, which is numerical modeling of liquefaction around marine structures. You can find more details about the project in this website. And yeah, so what do we do in our project is we develop a numerical modeling framework for liquefaction around marine structures, of course, in OpenFOAM. And this project also comprises of small scale and large scale experiments where they do experiments, and then like we will be validating our numerical models against those experiments. And at the right, what you see here is the case study that we wanted to do in our project. In that we have a gravity anchor mounted on a seabed, which is further connected to the floating offshore structures, what you see in yellow color, and that is further connected to the wind turbine. So whenever there is a waves, and then like there is a load, and then like the load is applied on the seabed, and then this causes liquefaction. And this is the failure that we wanted to predict in case of our numerical model. So the liquefaction can be broadly classified into two types. The first is residual, and then the momentary liquefaction. Residual, what I have been telling you before, it occurs in case of progressive waves. And so you have a periodic pressure variation in the seabed, and due to the alternating expansion and compression, that changes the shear stress in the soil, and this deformations in the shear stress will gradually rearrange the soil grains, and then the pressure inside the water increases, between the soil particle increases, and then whenever this pressure is greater than the initial effective stress of the soil, the soil behaves like a fluid. And the other case is the momentary liquefaction, in which it occurs mainly during the passage of wave trough. And for example, in unsaturated soil, the pressure gradients are very large, and then this larger pressure gradients allows to generate a lift in the top layer of the soil. And then whenever this lift is greater than the weight of the soil, then the momentary liquefaction occurs. This momentary liquefaction is a temporary process, and so we do not concentrate much in our project. So the diagram what you see here is the sequence of the liquefaction process, and how the liquefaction occurs is generally the pore pressure starts to build up, and as I told you, like once it's greater than the initial effective stress of the soil, then the soil starts to liquefy, and generally the initial effective stress of the soil is it's low at the top of the soil, and then like it's high at the bottom. Similarly, the pressure similarly the pore pressure starts to build up, and then like it's high at the bottom, and then it's low at the top. And at some point of time, the liquefaction starts. It generally starts from the top of the soil, and it progresses downwards. And at some point of time, you have, as I was telling you, the pressure gradient. There is a pressure gradient such that like high pressure gradient at the higher pressure at the bottom, and then lower at the top. So it drives the fluid upwards, and the soil particles starts to settle down at the bottom. That is known as that is the process when the compaction starts. So most of the literature right now, they are calculating only till the onset of liquefaction. But we in our project, we wanted to do the entire liquefaction sequence. So we would be predicting until the soil compaction. So this is the numerical model of our project, and you can see that this is nothing different from the case study what I was showing you before. So here you have a seabed, and then you have the gravity anchor, which is then further connected to the connected with help of rope forces. So generally, we subdivide this region into three different parts. First, we have the omega-1 region where we have the waves, and for the waves, like we will be representing in terms of wave equations. And then like we have the soil region where we represent in terms of a poroelastic solid with the incompressible pore fluid, and finally the liquefied region. So generally, we don't have liquefied at the starting of the simulation. So it happens after some time when it's pore pressure building up, and then like it is greater than the initial effective stress of the soil. So we don't have at the beginning. So at some point of time it changes, and we do get liquefaction. But the problem here is like it's not poroelastic solid anymore. So all the constitutive relationship changes. So we wanted to represent something different. That is, for example, a non-Newtonian fluid. So here's the bioequations. This is these are the equations for representing the poroelastic solid. There can be many different equations, but we wanted to make it. We wanted to have it very simple. So because like in the end, like we wanted to compare against the experimental results, and if we have a complex model, we would be having a large number of parameters, and it is very difficult to determine from the experiments. And yeah, so here we have two different equations. One is the pore fluid continuity, where you have the Laplacian of the pressure equal to the rate of change of volumetric strain and then the rate of change of pressure. And the rate of change of volumetric strain that tells the volume change due to the soil skeleton. And then the next one is the volume change due to the compressibility effects. And finally, the second one is the momentum balance. Here you say that the divergence of stress is equal to 0, and the right hand side terms actually comes from the normal pore pressure. And in these two equations, we'll be solving for the pressure and the pore pressure, and then the displacements. And from the displacements, we can have this linear equations in order to calculate the stresses in the soil. So since it is a poroelastic solid, it is just a linear equation. It's giving the stress strain relationship. So, but in order to have a residual liquefaction, those two equations are not enough, because because the pore pressure is instantaneous, and they do not calculate the rearrangement of soil grains. So the residual liquefaction needs the rearrangement of soil grains. So the shear stress and shear deformations would gradually rearrange the soil grains. So we have some. We need to calculate the accumulation of the pore pressure, and that can be calculated from this equation, something like this here. And then just to give you a idea about it, the small p, the pore pressure, this is the one that we get out of the bioequations, and then this is the pore pressure buildup that is building up the accumulation of pore pressure. It's going on. And here's the case study that I wanted to compared against the analytical results. So I have here a seabed, and the seabed, the length of the seabed is equal to 1 wavelength, and then if I talk about the boundary conditions, I have the wave equations on the top for the pressure, and then I have a traction free for the displacement, and then the pore pressure buildup, or the accumulation of pore pressure, is 0 at the top, and at the sides, since I have exactly one wave, I can use a cyclic boundary conditions on the sides, and then at the bottom I have an impermeable base. So I set the pore pressure and then the accumulation of pore pressure to the gradient of them to 0, and then I set the displacement to 0. And here's some of the parameters that I used in that. So I think I don't want to go much detail into it, and you can see from the results that I have an excellent agreement with the analytical results. And yeah, you can and this work is already published in the OpenFOAM journal, and please feel free to look into it. And the next one we wanted to do is the post liquefaction. So as I was mentioning you before, that once the soil gets liquefied, the constitutive relation changes, and then we wanted to do something different. So this is nothing different. What I've done is, like, I've just added the Navier-Stokes equations in here. So I have one additional equation for the momentum balance for the solid fluid mixture. And here, what you see here, like I have a term CL that is determining, that is an indicator function, so that whenever it is 1, I say that it is a liquefied soil, and then like whenever it is 0, it solves for the solid equations, or the poroelastic solid, what I have been telling you before. And one thing like I have to discuss here is the dynamic mesh. Like how I do is now I calculate for the accumulation of pore pressure from the equations what I was showing you before, and then I calculate the liquefaction criteria, and I go through the phase cut identifier. What it does is it goes through each internal phases in the mesh, and then like it will check for both the sides, the at the either sides whether the cell is liquefied or not. If there is a difference, for example, one cell is liquefied and the other is not, then it creates a phase between that. So after that, like it goes to topo changer, and which dynamically changes the mesh. And so I can change I can have a new boundary condition between the liquefied and then the non-liquefied regions. And this loop goes on, and then like after one iteration, like it again goes to check the accumulation of pore pressure, and then the loop continues. So I have a video here. Oh, okay. So here it is the dynamic mesh. So this is the soil region, and after some time the liquefaction starts. So the top part is starting to liquefy now. The red region is the liquefied region, and then you can see that a boundary is created between the liquefied and non-liquefied regions. And as the time progresses, you can see the liquefied region changes, as also the boundary between the liquefied and the non-liquefied region changes continuously. So the boundary conditions, what I have here is nothing different from the earlier one, but I have here a new liquefaction front, that is the liquefied, the region between the liquefied and the non-liquefied region. And I just simply apply a cyclic boundary condition between the solid for all the parameters. And again, I don't want to go much into detail for the parameters. And here I also have another video. So here it's the velocity vectors, and you can see that the top part of the soil is getting liquefied, and then like it behaves differently after liquefaction. You can see a big difference, that the velocity vectors are perpendicular on the top, and then like it rotates in the bottom. So here I just wanted to show you the differences in the pore pressure buildup in case of liquefied soil. So here, like I have three different curves. The one is the one which I use the bioequations even after liquefied region. So I use the Navier-Stokes equations, but I still use the bioequations. I just like wanted to see how much difference that it gets. And you can see that like it is comparable with the results. Like when I use the Navier-Stokes equations after liquefaction, I here have two different viscosities, and also you can see that it is okay. There is a difference when I use the viscosity. When I change the viscosities. So the last case study that I want to show you is a vibrating plate. So in which the soil, the soil, instead of waves on the top, I have a vibrating plate, and then like it shakes, such that like it generates the it applies the load on the seabed, and then like because of that, like the soil starts to liquefy. So the idea actually comes from this Cation rocking plate, where whenever you have a structure, and then like due to the structure, when there is a movement in the structure, that could whether that could affect the whether that could cause liquefaction. So in that, like in order to mimic the experiment, there is a small seabed like this, and then which is connected to the piston movement, and then this is connected to the anchor, and then like whenever there is a movement, and then this the top part starts to move, and then there is a movement in the seabed. So I also have another video here. So you can see that this is the case study that I wanted to do. So there is a vibrating plate on the top, that the other region is the seabed. So there is a movement in the vibrating plate, and then like that is causing the load on the seabed, and we wanted to study how much that how that does it cause the liquefaction because of that. And these are the parameters that I wanted to, these are parameters that I have used in this model. And I would also wanted to discuss more about the boundary conditions of the model that I've been using for this. And at the sides of the soil box, I just use the classical boundary conditions like the zero displacement and then the gradient of pressure to be zero. But at the contact surfaces, like I used a special boundary condition from OpenFOAM. There's a solid contact. So what it does is whenever this vibrating plate is in contact with the seabed, so it applies displacement, and whenever it is not in the contact, it applies a traction-free boundary condition. And here are the results. This is the shear stress. You can see that whenever there is a motion, you can see that the shear stress is high at the corners of the vibrating plate. And since the shear stress is very high at the corners of the vibrating plate, the liquefaction also starts from there. So this is the one for liquefaction, and then the blue region is the solid. And then whenever it starts to liquefy, you can see that the liquefaction is starting from the corners of the vibrating plate. But if you remember from the previous slide, you can see that this is the results from the experiment, but the liquefaction is actually starting from the middle of the domain, and then it is spreading outwards. But the problem we face is the displacement is very high at the corners of the vibrating plate, and that is causing that is actually causing the high shear stress, because like we have a linear stress strain relationship, but which is unusual in case of the experiments. So we can actually go with the different models, but we would need a large number of parameters in order to have a very complex model. So finally, I come to the conclusion. So what we have done is like we have developed a FEM solver that has been developed using OpenFOAM, which calculates the accumulation of pore pressure. And then this numerical model is validated against the pore pressure, shear stress, and the momentary liquefaction. And also, like I've shown you the results of the onset of residual liquefaction. And after the onset of residual liquefaction, you can see that the dynamic mesh we have used in order to separate the liquefied and then the non-liquefied regions. And in the liquefied regions, like we also apply this Navier-Stokes equations. The next steps, like what we would like to do is we wanted to validate our post-liquefaction model. So we haven't got any model to validate it. So any suggestions would be welcome. And also we need to numerically validate the case where I have the plate subject to the rocking motion. So even for that, like we have trouble in validating against the experiments, because in the experiments the liquefaction starts actually from the middle of the domain, and then we have for us like it is something different. And finally, we after that, like we will be validating our numerical model against the experimental results in the future. And here are the references. And finally, I would like to acknowledge co-founder Matera for funding this project. And thank you very much for your attention.
Are there any questions for the speaker from the in-person attendees?
Yeah, we have actually right now tried only with 2D, but since it's OpenFOAM, it shouldn't be any trouble having to move it into 3D. It shouldn't be a problem.
Are there any further questions? Please chat.
Okay, there is a question that are there any movies for the dynamic mesh? So I mean, the movie that what I have for now is the one what I've showed before. So it's the one, I mean, in the dynamic mesh, like I'm just creating a boundary or the boundary condition between the liquefied and then the non-liquefied regions. So that's the only movie that I have for now.
Okay. So.
No.
So I had a question that can it be, can your model be extended to a more complex case like offshore wind turbine base? Like, I mean, not offshore, but what I wanted to ask that can you couple FSI with that? Like the rocking motion that you showed, can it be a structure which is moving due to the effect of the wind, and then so can the model be extended to a problem like that?
Yeah, this model, I mean, the question is, can the model can be extended with the help of rocking? I mean,
yeah, so the prescribed motion that you gave and the liquefaction started,
yeah,
can it be a flow induced vibration of the body?
yeah, that can be extended.
In fact, we need to do the
Right.
because we are the model
And
that's kind of
more interested. I'll look into the OpenFOAM journal paper.
Yeah.
Thank you.
Thank you.
If there are no further questions, let's thank the speaker. Very nice presentation.